Right. So welcome everyone. Today we're very happy to have Leonie today. So she was at Oxford, I think already it's now more than a year ago, right? She did her master here at Oxford. Well, here, in the real Oxford. And now she's in Aachen, working with Michael Schaub, who's also, of course, an Oxford familiar. Today she'll talk to us about her work, I think that was done with Renault as well, about no higher order effects without nonlinearity. So please, Leonie, the mic is yours.
Okay, so yeah, welcome everybody to my talk about no higher order effects without nonlinearity. Yeah, and first of all, thanks a lot for inviting me to present at the seminar. That's actually pretty cool, and I was really excited because it was one of my favorite events when I was in Oxford, and yeah, so I'm really excited to present here my work that I did there. And just as a small overview, in the first part of my talk, I will, that will be based on a paper I have written jointly with Andrew Meller and Renault, and a conference version of that same paper for which Michael Schaub joined, about multibody interactions and nonlinear consensus dynamics on network systems. And then in the second part of my talk, I want to give a small introduction to what we extended this project to, which was a collaboration with Neuhäuser, Srabude, and Renault again, where we extended the model that we introduced in the first part to hyperedges of cardinality of any size. So just to start with, let me give a short introduction into modeling social dynamics and what that has to do with higher order interactions and what made me curious about it. So networks have recently, or not just recently actually, but have become very popular to investigate social dynamics. And well, that's great, but there is a small problem. Sometimes networks fail. And I mean, we're in the network seminar here, so we all love networks, but there's certain high order dependencies in the interactions in a system. For example, group or multi-body interactions, which a pairwise network setting simply cannot capture. And the question we asked ourselves is only when does this actually become important for the overall dynamics of the system? So when do we actually have to bother? And higher order dynamics can occur in all kinds of areas, but I specifically want to focus on social dynamics here, such as consensus dynamics. And I introduced a three-body consensus model to investigate the possible higher order effects of these multi-body interactions. So to start with, dynamics on conventional networks can be classified as pairwise interaction systems, where agents have local pairwise interactions, and the overall effect of the interactions on each agent is the sum of the pairwise interactions with other agents. And in contrast to that, a three-body interaction system takes into account the joint influence of triangle neighbors J and K on node I. And that is then described by an interaction function Fijk. And therefore, in contrast to the pairwise case, the interactions between node J and K here become relevant for their influence on node I. And in our work, our main goal was to examine if and then under which conditions three-way interaction systems can lead to higher order effects that cannot simply be explained by the pairwise interaction system. So that is operating on the underlying network of the triangle structure. And so why is this important or interesting? In sociology, it is well known that the dynamics in a social clique are determined not just by the pairwise relationships of its members, but also often by complex mechanisms of peer influence and reinforcement. And just to make that a little bit more visible, I have a little example here. So the relatable example, I guess, of everybody of joint parental discipline here, you can see that there's a link between parents, which can, for example, model a shared opinion, and that enables reinforcing dynamics that lead to a stronger influence on the child, which is then not captured by the independent pairwise influences in B. So therefore, higher order models such as the previously introduced one, so the three-body interaction model, and we called it 3CM, just so that you know, and when I will talk about this in the future, additionally account for that effect of the group as a whole. And we now want to investigate how these interactions can lead to effects that cannot be explained by pairwise systems. So in order to do that, let us introduce an interaction function that can capture this reinforcing effect, like in that example from before. And that consists of a linear consensus term and an influence function S of x. And that captures the higher order influence of the triangle nodes J and K on node I. And it does that by scaling their pairwise influences by their state difference. And that is then modulated by the scalar influence function S of x. And if we now assume that S of x is monotonically decreasing, for example, an exponential function with a negative exponent in the future, we can see, like in the small example, that node P and K therefore reinforce each other because they have very similar node states. And in contrast to that, K and J hinder each other because they are very distinct in their node states. And this also models the example of joint parental discipline from before, because when parents support each other in disciplining a child, if they have very similar viewpoints, and they might hinder each other if their opinions conflict. So if S of x is constant now, the interaction function is just a linear combination of the diffusive couplings on the two edges. And the whole dynamics then can be rewritten as a two-body dynamical system after a proper rescaling of the adjacency metrics. So then in that case, we are basically dealing with network dynamics. And we can now look at this in a little bit more detail, because if we rewrite the model to relate it to a weighted version of the network Laplacian of the underlying network of the triangle structure, in order to do that, we first have to define a weighted adjacency matrix W. And the entries Wij account for the higher order effects on node I over the edges, over the 1h Ij. And the weighted Laplacian is the matrix representation of the nonlinear dynamics. And if S of x is constant, which gives us linear dynamics, this operator is not time dependent and reduces to the so-called motive Laplacian for triangle motives. And that has been introduced in the literature before. And we are then basically dealing with rescaled pairwise dynamics. And in the nonlinear case, even if it seems like a reformulation to a pairwise system, don't get confused, because the entries of the weighted Laplacian are then still dependent on the node states of the neighboring triangle nodes, which creates the higher order dependencies on the triangle structure. So we conclude that in order to reveal any genuine higher order effects of three-way interactions, which cannot be explained by the underlying scaled pairwise interactions, we must have nonlinear dynamics. And this general result of our work underlines that a triangle topology alone does not guarantee that higher order effects will appear, but that also heavily depends on the type of interactions present. Yeah. And after all of these theoretical results, let us now look at possible effects that may emerge from this model. And we do that in three different scenarios. We first apply a mean field approach to eliminate all topological effects of different distributions of triangles in the systems, and just consider a fully connected system and see what happens then for different initial distributions of node states. And we then additionally take into account asymmetric topologies by examining two connected clusters, which can, for example, in an application, they may represent polarized groups. And in the last scenario, we see a joint effect of initialization and topology, which then results in a timescale separation of the dynamics. And what are we generally interested in observing? So we generally look at consensus dynamics. So we are interested in if and how a given system reaches consensus, which means that all node states have the same value. The consensus value equals to the initial average of the system, and that is conserved on undirected networks. And now we investigate in which cases the consensus value is affected by the higher order dynamics in our three-way interaction system. There, as we can see here, the average state is only conserved if the weighted adjacency metric is the weighted adjacency matrix is symmetric for all times. And this is only generally true for linear dynamics when S of x is constant. And that is the theoretical result from before, that we're then just dealing with scaled network dynamics. So then this conservation of the initial average is also given. For nonlinear dynamics, that symmetry is generally not the case, but depends on an interaction of initialization, triangle structure, and interaction function. And now we want to look at what can happen when those imbalances occur. So in order to investigate how the nonlinearity of our model affects the conservation of the average state, we first consider a mean field approach. So just a fully connected hypergraph. Oh yeah, and as S of x, we take the exponential function with a negative exponent, so a monotonically decreasing function. That displayed condition here reminds us when the weighted Laplacian is symmetric, so when the average state is conserved for all times, as we have derived before. And in a mean field setting, we expect this to happen for an initial node distribution with an average equaling to 0.5, because then all nodes are connected and the higher order effects balance out initially. And because the system is otherwise also symmetric because it's fully connected, that then expects to hold for all times t. And this motivates an assumption now that a biased asymmetric initialization, distinct from 0.5, is required for higher order influences on the average state of the system to occur. And yeah, the average state then evolves in the dynamical process, which depends on the influence function. So as similar nodes reinforce each other, the shift is enlarged. And the numerical simulations we performed confirm exactly this. So this shift towards the majority in the initial population is present only for the nonlinear case, for the reinforcing interactions, and not in the linear case, as you can see there. And that reflects how peer pressure that is modeled by nonlinear and reinforcing dynamics, for example, can cause opinion drifts in the population. And those opinion drifts would not be present or captured by a network setting. So in scenario B, yeah?
Could I ask a question?
Yeah, of course.
Previous slide. So what if this S of x, if that's an odd function, wouldn't you then also have the conservation of average state?
No, because the S of x is just the scaling function of the wait, if you go back, where is the initial? There we go. So the S of x just scales the diffusion process on the other edges. So if the initial states are distinct enough, then that always reinforces in one direction and not in the other, and not dependent on if it's an odd or an even function.
Okay. Okay. So that's also something to do with the second part, then, I guess.
Yeah. Yeah. Exactly.
Yeah. Yeah. Okay. Thanks.
Okay. Okay. So in the second scenario, we now investigate the influence of asymmetric topologies. So we're not in the mean field case anymore. We have clustered settings now. So two connected clusters that consist of the same number of nodes. So, and one cluster is initialized with state 0 and the other one with 1. And the clusters are then connected by a set of triangles, and we call a connecting triangle between cluster A and cluster B directed towards cluster B if A contains the inner edge, so the majority of the nodes of that connecting triangle. And due to the consensus in cluster A, which contains the inner edge now, the diffusion on the two outer edges of the connecting triangle is accelerated. And on the contrary, the influence in the other direction is inhibited as the two outer edges then are damped. So the diffusion there is damped due to the large state difference between the clusters. And this leads to directed dynamics between the clusters, even if the system itself is undirected. And therefore, even if the initial average in the system is 0.5, because the two groups have the same size, which led to a conservation of the previous, of the initial state in the previous mean field case, the asymmetric connection now leads to one cluster kind of conquering or dominating the other. And we can investigate that further if we define a directedness parameter P, and that is the fraction of triangles that are directed towards cluster A. And we can observe a shift in the final consensus value from the value of cluster A to the value of cluster B. And that can be seen here in A. And this is expected for reinforcing dynamics as the connection is maximally directed towards cluster B for P equal to 0 and towards A for P equal to 1. And here in B, you can see that this also influences the convergence speed. Because the more directed the connection is, the higher is the acceleration of the dynamics, and the simulations also show that there's higher standard deviations for values close to P equal to 0.5. And that indicates that the dynamics are very sensitive to even small deviations from a balance in the initial topology, which may result from different distributions of the triangles on the network. And that can then lead to large differences in the consensus value. So in the former setting, I've now shown you two groups which were the same size. And there is also a conference version of that paper that I'm presenting right now, where we considered a small extension on something called minority influence. And in this new setting, now one cluster forms a minority. And in our setting, for example, we again take cluster A with initial state 0 and B with 1. And a directed connection towards cluster A. But now A has twice as many nodes as B, so forms the majority. And if we consider linear dynamics, A dominates the opinion formation as expected because the initial average is conserved and A represents the majority. And now, the interesting case of the reinforcing dynamics, the minority cluster dominates the opinion of the majority cluster. And even kind of shifts it over to its side. And in the context of opinion dynamics, this can model something called minority influence, which basically says that a small group can dominate the formation of an opinion, not because of their size, because they're simply smaller, but due to their internal cohesion and because of their connectedness in the system. Okay, but let's go back to the case of two clusters of the same size and have a deeper look to the type of initial distribution of the node states. To achieve directed dynamics between two clusters, one thing that has to be given is that their initial states have to be sufficiently different to accelerate the diffusion in one direction and not in the other. And in the case of binary initialization, like before, this difference was maximal. And what we do now is we initialize both clusters uniformly randomly over separate intervals, so 0 to 0.5 and 0.5 to 1. And we thus observe a timescale separation of the dynamics. The clusters are internally fully connected, and therefore intercluster dynamics are generally more inhibited in the beginning due to the differences of the initial cluster means. And therefore, we first observe symmetric dynamics within the clusters towards the specific means of the two clusters, and then asymmetric dynamics between the two clusters. Yeah, which brings me to summarize the key messages of that first part of my talk or of that paper. So what have we done? We have introduced a new model for consensus dynamics on three-body hypergraphs, which can be used to show that group interactions reveal higher order effects that are not captured by pairwise network models. And I think the most important fact that you can see here is that we find that non-linearity is essential to reveal genuine higher order group effects. And for linear interactions, the dynamics can always be rewritten in terms of the network, of a scaled version of the network, but in terms of the network. And moreover, these higher order effects that result from reinforcing group effects with that specific influence function then can lead to interesting shifting phenomena that can be interpreted in different sociological interpretations, and that can only be described as an interaction of initialization, higher order network topology, and the nonlinear interaction function. Yeah. And yeah, as I said, this first part of the presentation is based on a joint paper with Andrew Mellor and with Renaud. Yeah, and first of all, thank you for the great collaboration. That was honestly a lot of fun to work on that project. Kind of also the project that made me do a PhD in the first place. And yeah, actually it was so much fun that we did not stop there and extended this work. And the next part of my talk is going to be about that extension. Yeah, but maybe I'll pause here for a second, just see if there's any questions. Of course, you can also ask questions in the very end, but maybe.
I was gonna ask you to stop to ask a question, so it's perfect timing. So I was wondering, related, maybe I'm not such an expert like Carol, but I was wondering if this decomposition into the two separate terms plays any role. The S part, which is the one where you put the nonlinearity.
Yeah.
But what about how you write it was a linear combination, right, of the other nodes in the triangle. Did you explore that? Did you change it?
So we look at consensus dynamics. So we wanted to conserve that diffusive coupling on the edges and just see how like a nonlinear scaling of that diffusion dynamics plays out. So you can obviously take a completely different nonlinear function. But we didn't explore that. So we took that diffusive coupling, which is then turned into a nonlinearity by that scaling influence function to generally look at a general consensus dynamics and not something completely else.
Okay, thank you.
Maybe slightly related to that, I had a question. Just do you think it's easy to generalize this form to more than 3 bodies, where you have like one scaling and then some sort of diffusion between the others? Or?
That's exactly what I'm going to talk about in the second part.
Nice.
So great question. Thank you. Yeah.
Okay, thanks.
Yeah, so perfect question to lead over, I guess. Anything else for now, or should I go on and then see in the end?
I think you can go on.
Okay. Okay. So these extensions that I'm going to talk about now are generalizing this model to hyperedges of any cardinality, and they are based on joint work with Neuhäuser, Srabure, and Renaud again. And yeah, I just want to thank upfront for the great work. That was really cool to go on with this. And what did we think was interesting? So 3-body interactions are great to make a point about general differences of 2-body and multi-body interactions. And we derived a lot of theoretical nice results from this kind of 3-body toy model from before. But actually, as you said, we would like to have a more general model for arbitrary group sizes. So in this follow-up work, we generalized 3CM by proposing a multi-body consensus model for opinion consensus on hypergraphs with hyperedges of any size. And we then explore different versions of interaction functions and investigate different sociological mechanisms. So to start with, a general introduction, let us first define general diffusion-like processes on hypergraphs. So if we have an hyperedge E alpha, which involves the node set alpha, we denote by xi E alpha the effect of an hyperedge E alpha on the derivative xi on the state of the node I. And the complete diffusion-like process is then obtained by linearly combining the effect of each I hyperedge on that respective node I. And when the modulating function for node I is the same for all hyperedges and also symmetric for all nodes in one hyperedge, then we can derive that weighted Laplacian that we had before in the 3CM part, exactly equivalent to the case of 3CM. And therefore, I will not go into detail here. But that confirms that the result we had before, that nonlinear interactions are necessary for higher order effects, is also holds or generalizes to arbitrary hyperedge size. And Nevertheless, there are different ways how to incorporate that nonlinear scaling function that we had in the 3CM case into our model. And in order to investigate the different effects that come from those different incorporations, we introduced a new general model in this work, which is called MCM, the Multibody Consensus Model. And how does that look like? Big and scary. So just to explain this a little bit, that's MCM. And what happens here is that the effect of an hyperedge E alpha on the participating node I is modulated by two different scaling functions, S1 and S2. And these are two facets of the model, and they have different, well, both mathematical properties and sociological motivations, which are captured by their arguments. And to explain this a bit further, S1 is a function of the distance of xi to the mean state of the hyperedge, and it determines the rate at which that hyperedge influences its state. And therefore, it modulates the competing effect of different hyperedges on the same state of, or on the state of an incident node. And Si2, in contrast to that, is a function of the distance of a participating node J from the mean state of the hyperedge excluding I. So therefore, it determines which nodes inside of a single hyperedge are the most influential. And that second part, Si2, is a direct extension of 3CM. And we can explore two variants of that model by holding the two functions constant respectively. So we can derive MCM1 and MCM2. And MCM1 is that kind of model facet that modulates the competing effect of different hyperedges on the incident state of a node. And MCM2, in contrast to that, is the extension of 3CM, the direct extension of 3CM. And we now look at those two model facets separately in order to see the differences that emerge from effects from the inference functions S1 and S2. And therefore, from the difference in incorporating nonlinearities into the model. So in a simplified case, we can even do some analytical mean field analysis for MCM1. But I will not go into details here, but start with the numerical simulations straight away. But they just, so that you know, those numerical simulations confirm the analytical results, and you can look at the paper if you're interested in those. So for a monotonically increasing modulating function with lambda bigger than 0, we see that the mean state shifts towards the initial majority, and on the other way around for lambda smaller than 0 for MCM1. And this was actually surprising at first, and I must admit that I first thought that there is a bug in the code, or we confused the sign of the parameters or whatever. Because while MCM2 is a direct generalization of 3CM, MCM1 shows the exact opposite behavior, despite the same choice of the modulating function. And that can be seen if we look at the results for MCM2 here. And because they're exactly the other way around. And that underlines the distinct nature of the two modulating functions, and that it actually makes a huge difference how to incorporate the argument of the nonlinear scaling function into the model and what kind of effects that has on the general process. But let's now turn to the sociological motivation of the two models. And let's start with MCM1. So recall that this model determines the rate in which different hyperedges influence a certain node. So if we choose S1 to be a monotonic function, a decreasing function can represent an individual who is less influenced by groups with opinions very different from its own than by groups with similar opinions. And this can be thought of as an individual that resists change, or some form of stubbornness. And on the other hand, an increasing function, so with positive lambda, can be thought of as representing some kind of gullibility. And yeah, this is managed by changing the parameter lambda in the function. And in the numerical experiment on a fully connected hypergraph, which is initialized with stubborn nodes with value 1 and gullible nodes with value 0, we observe a consensus shift towards the stubborn nodes. So that underlines that, yeah, important effect of that first model facet, the MCM1 facet, that individuals can influence other members of a group more while being resistant to their influence. So stubborn nodes can basically be influencers or some kind of trendsetters and pull other nodes towards their opinion. And yeah, in order to investigate effects of the whole MCM model, we can also combine the two facets. So both include interactions within a hyperedge or the joint influence of all of the hyperedges. And here we build on a theory called social judgment theory. And well, that social judgment theory classifies different opinions in 3 theories, so 3 categorizations basically. So the latitude of acceptance, that means that if other opinions are sufficiently close to your own belief, they are accepted, and then the beliefs shift towards the new opinion. So that describes some kind of assimilation if you're close enough in opinion. Then the latitude of rejection. So if the other opinion is too far from your own and is therefore completely unacceptable, that even leads to the fact that nodes' opinions shift away from each other. And if the other opinion is neither sufficiently close to be accepted nor different enough to be repulsive, we then have non-commitment. And yeah, we therefore define 3 thresholds: that of acceptance and rejection, not 3, sorry, 2 thresholds. And the higher the involvement of a node in a certain topic is, the smaller their latitude of acceptance and non-commitment. And in the following numerical experiments, we will investigate 3 different cases: high, medium, and low involvement. And we, as I said, we also include MCM2 in this model, so we don't hold any function constant. And MCM2 is simply modulated by an exponential function, which describes the interactions of an individuum with each group, and yeah, which basically then involves peer pressure dynamics. Okay, so what happened in the numerical simulations? We look again at 2 fully connected hypergraph blocks, and those 2 blocks are connected by a set of hyperedges, and they are both initialized randomly over 2 separate intervals. And yeah, and we see what happens if we apply this model. So as you can see, in the case of high involvement, we observe a split into 2 polarizing groups, and groups moderately invested with moderately invested people have some kind of an iterative consensus process where they first yeah, evolve into 2 consensuses in their respective blocks and then eventually reach global consensus. And in the case of low involvement, global consensus is almost always reached. And we also extended those numerical simulations that before that all were performed on synthetic hypergraphs on real-world hypergraphs. And in our case, we used the sociopatterns dataset. And yeah, I think you're probably all familiar with that, but for those who don't know that dataset, it records face-to-face interactions with a in different settings with a temporal resolution of 20 seconds. And in that data set, we can check if people are interacting as pairs or as a whole group in each of those time windows. And we here define genuine group interactions and hyperedges if they appear more often than 5 times. And we look at the fraction of extreme nodes, measuring polarization in the outcome of our simulations. And yeah, we can see in the results that only in the low involvement scenario of our model, the polarization is, our fraction of extreme nodes is low over all of the data sets, and in the other ones, it isn't. And in the, I think, yeah, in the last numerical simulation setting that I want to show you, we performed simulations to investigate the role of the stubbornness parameter in the model. And yeah, we did this for the classroom hypergraph of the socio-patterns dataset. And we restrict us to only acceptance and not rejection. So there's only an acceptance parameter and not a rejection parameter in the model. So students interact much more with their classmates than with others. So we can randomly, leads to this kind of block structure of the classroom setting of the socio-patterns hypergraph. And we can randomly pick some nodes in each block and initialize all of those nodes with binary states, 1 for the stubborn nodes and 0 for the others. And that then gives us an initial average of the system of 0.2006, so basically 0.2, more or less. And nevertheless, even if that is smaller than 0.5, so leans towards the initial majority, the mean opinion of the group shifts towards 1, which indicates that the presence of a few stubborn individuals already has a significant effect on the consensus of the whole group. And as you can see there, also the magnitude of the stubbornness parameter, of course, has a high influence on the dynamics. So let me summarize our main results of this second part of my talk. So we extended the 3-body interaction model from before, and we have proposed a general nonlinear model for consensus dynamics called MCM 1 and 2, or the general model MCM, where different model ingredients are associated with different sociological mechanisms. And we can differ between 2 facets of this model, MCM1 and MCM2, and they differ in their sociological motivation and in their argument of the non-linearity, which then leads to different simulation results and effects of the dynamics. And we have studied this. We have studied some sociological phenomena motivated by theory from sociology, oh man, yeah, you know what I mean? Which on real world hypergraphs, which then leads to interesting higher order effects that would not be present in settings of consensus dynamics in network settings. Yeah, this is the preprint if you want to look at it. And this brings me to the end of my presentation. And yeah, thanks for your attention. And those are the references. And yeah, to end with, I just want to say thank you to everybody that I've worked on in these projects. It was really a lot of fun. And yeah, if you have any questions, then ask me anything that comes to your mind.
Thank you, Leonie.
Thanks a lot, Leonie. So if there's any questions, please go ahead. You can also put something in the chat if you prefer.
Oh, I cannot see the chat. Then you have to read it out for me.
So maybe just a question. So do you plan to try to investigate the possibility to use these models with respect to real data? Because I know, because there have been so many models for opinion dynamics, consensus dynamics, some that are linear, others that are nonlinear. And do you think that there might be one day the possibility to test some of these models and to really calibrate maybe some models based on real data sets?
I'm like constantly thinking about it. I would love to, because it always, like, this is all really interesting modeling, but I think you kind of have to go this step further to try to fit it to data at some point. And I've thought about different settings in which that could be possible somehow, like reaching from online experiments to I don't know. So basically, if you have those shifts in the initial state distribution over the whole consensus process, that can always be kind of an indication that a higher order effect in that direction is present. That would not be captured by normal consensus process. But obviously, in order to really pin that down to those dynamics, you would kind of have to have the network setting with independent interactions at the same time. Yeah, I've thought about it a lot. I think in online experiments, it could work out pretty well, that you basically let people interact in groups at the same time and also distribute them the same amount of neighbors in some kind of interaction process. But yeah, I mean, I haven't found data sets yet which would be, if anybody has ideas in that direction, please reach out to me. That would be great.
I was going to ask the same question, but I guess the problem is how do you find a data set that fits into this framework, right? Where you track the opinion.
Yeah, I mean, the thing is, first of all, obviously, it's, right? Yeah. I think that's a general problem in opinion dynamics to measure the opinion in the first place, or the outcome of some discussion process. What can be interesting is, for example, look at minority settings or something like that. Sorry?
No, nothing.
I think one way that might be possible is using NLP, actually. So not just, I mean, sentiment analysis has been used in the past to approximate what might be some kind of opinion. Again, it can depend on the context that you're looking at. But even just a negative or positive valence, but also some more specific, if you're looking at a pretty narrowly defined concept, you can probably use NLP to extract certain, using different lexicons or different other established frameworks, use these models, these language models, to extract opinion stuff. That's kind of something I've been looking into, so if we can chat more.
Yeah, that would be cool. That sounds good. Thank you. Yeah, one setting I've also Sorry,
hi Leonie. I was going to ask a question, but then you carried on.
Go for the question first. That was like an idea that I had. But
I was going to ask, really nice talk, by the way. I always like these opinion dynamic figures. They look good. Anyway, I was wondering how small a network you need in principle to get something like this to work. Because if it works in a very small context, I could imagine you could just create a data set, like create some hypothetical scenario, get 100 people together, connect them in some, I don't know, online way, and then see what happens. You can have these sort of, and I think that would be fun to try if it works in small enough settings.
Yeah, it definitely does. I mean, all of those kind of synthetic examples are really small networks as well, because the well, that doesn't really affect the outplay of those nonlinear reinforcing dynamics. So that would be really cool if you could create some kind of experiment doing this. So following up on that, like one thing that I've, for example, thought about was one of the teachers of a class in the university I've been in before, they had some kind of peer review system for students where they kind of created, they had to join up in groups to create reviews for classwork, and that was distributed in an online way, randomized in groups. And you could do that, like, so something that I thought about was you could either make them interact as a group and agree on marks for their classwork, or you could make them mark individually or in pairs of two or whatever, and then see the difference that come out from that. So that was one setting, for example, that I had in mind. Haven't got to actually try it yet, but that's the nice thing, that it actually does work in small settings already.
That's great. I don't know. I think about it because I'm
Cool.
sure there must be some nice way. I know. What's his name? Andrea Baronchelli in City.
Mm-hmm.
Is it City or Greenwich? Well, one of the London ones. He's done. Yeah, I'm trying to remember from like 2 years ago now. But he did similar opinion dynamics work, and they did precisely this. They got 100 people together, created some online network for them to interact within, and they use that to verify their model. So it's definitely been done before. If I can, I would tell you what it was if I could remember the name of it, but it was definitely Andrea Baronchelli.
Okay, I'll look that up. Thanks for the tip.
And I think it was in Science or Science Advances, one of those.
Okay.
But yeah. Anyway, great. I enjoyed this.
Cool. Thanks.
I also have a question. It's a bit less on the sort of application side, but more on the model itself.
Mm-hmm.
Is it correct that like the first model, it's with 3 bodies, it's sort of a directed motif, so that you look at the influence of 2 other nodes, or it's like fully symmetric in a way?
No, it's symmetric. So it's an undirected system. So there's no directedness. I find the same model also for directed motifs, but then you kind of have to make sure that you have rooted motifs in the node that you look at the influence on. So the derivative of the node state that it's directed towards that node, or you have kind of circular motifs or whatever. So then it all becomes a little bit more complicated, but in theory, it's also possible to define it for directed networks, but that is all, undirected settings. That's actually the cool thing, that it's an undirected setting, and still you can have those directed dynamics just coming from those interactions of topology and initialization.
Yeah, that's a bit why I was asking, because indeed in this figure it seems like you have this direction, the one between the 2 groups, but then indeed that's something that's not just direction from the network, but from
exactly. So if you look at this, is maybe a bit confusing. Maybe I have to rethink that figure, but this actually doesn't mean that the edges are directed. It just means that, can you see my mouse?
Yeah.
So it just means that because those 2 node states are so close, and therefore the scaling, so this part is big, the diffusion on those 2 edges, which is symbolized by this, is enlarged, and here it's inhibited. So it's basically just representing how strong the diffusion process on those edges is, those arrows, and not that it's a directed system. And then also in those clusters, those arrows here also just symbolize that because these 2 nodes have the same node states, this is enlarged, and here it's inhibited because they have different node states. So it's all not directedness of edges, but basically just showing in which direction those dynamics are.
But again, that's due to the non-linearity somehow.
Exactly, yeah. It's
otherwise
an interaction of, it's just this term here. Wait. It's just this term scaling in different ways because it's dependent on the node states of those 2 nodes.
Yeah, that's cool. So you could in a way think, maybe you don't need directed networks if you just cleverly use the or define the dynamics or something. Yeah. No, cool to think.
Yeah, that was cool.
Okay, so I guess if there's any other questions.
If I can't. Yeah. Hi, Leonie. Good to see you again. Really cool work. I missed the first part of the talk because I was struggling to sign in. So apologies if this is a stupid question, but I was wondering about the non-linearity.
Mm-hmm.
Is there any particular non-linear functions that you can use, or can you extend this to any non-linear functions? What are we thinking in terms of the types of non-linearity?
So basically, we're looking at non-linearly scaled diffusion processes. So basically, the form of the function we're looking at is this specific form. But for S of x, you can basically take anything as long as it's monotonically decreasing or increasing, which is then, either inhibiting or reinforcing dynamics. You can also, we've also in the paper actually done some things with S of x being the Heaviside function, which is also really interesting because then you have like kind of a switching between linear dynamics and then nonlinear ones. So something like, okay, if somebody has an opinion too different to mine, I'm not even talking to them, and then from some point on you kind of start agreeing. So that's also interesting. But then in some special settings, a consensus would not necessarily be reached anymore. For example, if all nodes are too far apart for the threshold of the Heaviside function or something like that. But that would be an adaptation of that, for example.
Yeah, so you're particularly thinking of monotonic functions.
Yeah, so for the S of x here, well, yeah, we also did some things with Heaviside functions, but yeah, then you might run into scenarios with no consensus. But I mean, the in the second part, the social judgment theory one. Yeah, I mean, this is not monotonic anymore, so. That also creates interesting scenarios then, but we just have simulations for that then, so that you not always reach global consensus. Yeah, but the basic form of it is always some diffusive coupling with a nonlinear scaling. And then in the multibody case, that nonlinear scaling can be dependent on different forms of arguments, which then changes the behavior.
Cool, thanks.
And also see that Max has put the reference in the chat.
Ah, cool. Thank you.
Amazing. Before. That's nice.
That's great.
So next time we have you for a talk with your experimental data.
Give me a month.
I'll already invite you for next year. Okay. It seems there's no more questions now. Otherwise, please do. Otherwise, let's thank Leonie once again for the really nice talk. She covered a lot of things, so it's always nice to have.
Thank you.
Thank you.
Thank you, Leonie.
And then we'll see everyone again next week. That's the last one of this term. Ah, no, wait. We didn't have a speaker, right? Is it next week? Yeah, so unfortunately, we're doing this fresh from the archive series now.